صباح الخير. أنا Carol Bier in San Francisco, California. It's a deep honor for me to be here addressing you, and I'd first like to thank the authorities of the United Arab Emirates, of Fujairah, and the School of Calligraphy and Ornamentation, as well as those who organized this conference. Thank you all. Thinking about geometry in Islamic art. In anticipation of a book manuscript I have written that is awaiting publication by De Gruyter in Berlin, I want to begin by considering what I mean by number, shape, and the nature of space, which is the book's subtitle. It is really very simple and has to do with patterns. And by that I mean a pattern, a unit that is repeated according to a systematic organization. Here the unit is a square, repeated along horizontal and vertical lines, or axes, which establish a grid. A square grid having 90-degree angles at the points of intersection of the horizontal and vertical grid lines that define the square units. So you see that the unit repeated makes a pattern, and that the pattern has a set of properties and relationships that result from its making. In this case, the square units rest on an edge or side. But one could also set those squares on point or vertex, which establishes a grid, but rather than being orthogonal with horizontal and vertical axes intersecting, it is oblique, an oblique square grid. The units are still square, and the axes intersect at right angles, but the lines are neither horizontal nor vertical, but all diagonal. So some of the properties of the pattern have changed, but both patterns are tessellations of a regular polygon having 4 sides and equal angles. A tessellation is a pattern that covers the plane with no gaps and no overlaps. Likewise, we may superimpose one square over another square at 2 different orientations, such that we create an 8-pointed star. The 8-pointed star is then the unit that is repeated, but it does not tessellate the plane. You can see the gaps in between the repeated units. The gaps are all the same. So this is called a semi-regular tessellation, because with 2 shapes, the 8-pointed star and the pointed cross forms, there is a tessellation that covers the plane. Similarly, with a triangle, we may repeat it in one orientation along an axis. No, there are 3 axes in 3 different directions and create a pattern, but it has gaps. 60 degrees is the operative angle. If we discount the color, here black and white, it is also a tessellation without gaps or overlaps, thus establishing an isometric grid of equilateral triangles. However, if we combine the 2 colors into one shape, it makes for a rhombic grid with axes crossing in 2 directions, not 3. You can see that there is lots of room for play in making these patterns, and it is really playing with space in 2 dimensions, the plane. And if we superimpose one triangle upon another with opposite orientations, we create a 6-pointed star as the unit to be repeated, introducing 120-degree angles. These forms do not tessellate, but again form a semi-regular tessellation, with 2 shapes forming the tessellation, here unfinished. If you look closely, perhaps you will see that the second shape is a combination of 3 rhombuses, Mitsubishi, that is the negative space, Mitsubishi in Japanese, and the logo of the car by the same name, meaning 3 diamonds or 3 rhombi. And circumscribing each 6-pointed star is a hexagon, with the hexagons together in the pattern intersecting. So this is what I mean, briefly, when I say number, shape, and the nature of space, referring to 2-dimensional space. 2 more quick examples before we move on show the unit as a hexagon, repeated on edge on the left and on point on the right, demonstrating how spatial relationships shift as the pattern is formed. If we conceptually focus on the centers of each of these units, repeated in the variety of patterns that we have thus seen so far, based on regular polygons, they are each circumscribed conceptually by a circle. The center of the polygon is the center of the circumscribing circle. The centers combine to form a square grid or a triangular or isometric grid, illustrated here by tight packing pennies. Circles, when tight packed, naturally combine in only 2 ways. One method yields centers that form a square grid, as you see on the left, and the other method yields centers that form a triangular grid, as you see on the right. These 2 grids, or means of packing tight packing circles, yield 2 systems of proportion, characterized by Isama Said in 1993 as the root 2 system based on the square root of 2, which is the diagonal or hypotenuse of a square, or the bases of a right isosceles triangle with 45, 45, and 90 degrees, which you see on the left, and the root 3 system, as Said calls it, which you can see on the right, based on the altitude of a right triangle that is half an equilateral triangle, with angles of 30, 60, and 90 degrees, which yields the square root of 3. Such basic mathematical considerations underlie the play of patterns in Islamic art. As we have seen, selecting centers in a triangular grid may establish a rhombic grid or a hexagonal grid. The triangular grid lends itself to 6-pointed stars and hexagons. The square grid often yields 8-pointed stars and cross forms. Lines and angles may then be established to create more relationships of stars and polygons. First, connecting lines. Connecting and erasing lines may produce interlaced patterns, and connecting centers to form lines and angles or highlighting curves, many seemingly complex patterns may be generated from simple algorithms. These aspects of geometry are all based upon Euclid's Elements, written around 300 before the Common Era, beginning with the first proposition of Book 1, which concerns the construction, as you see in the upper left, of an equilateral triangle. The foundational work of Euclid, Al-Euclidis, was translated into Arabic and circulated widely throughout the Islamic world. The relationships established by repetition are all based upon the relationship established by repetition are all based upon the invariant proportions of circles, the ratio of a radius or diameter to the circumference, which remains constant no matter how large the circle. We refer to this irrational number by the Greek letter pi. Euclidean geometry also underlies the field of astronomy, but it is further developed in Islamic lands. And the many instruments and equipment used by astronomers, here represented in a manuscript illustration of the Observatory of Taqiyuddin in Galata in the late 16th century, is the key instrument for drawing circles, the compass, as you see on the right, or a pair of dividers. The one illustrated dates from the Seljuk period. It was excavated at Rey in Iran, held today in the Penn Museum at the University of Pennsylvania in Philadelphia. Let us move now to a brief presentation of the content of my books, Geometry in Islamic Art, Number, Shape, and the Nature of Space. Beginning in the 11th century of the Common Era, I seek to identify a new conceptualization of the spatial domain in two dimensions that is evident in the architectural ornament beginning with the Masjid-i-Joma Isfahan, I think. It is also apparent, I argue, in the two tomb towers at Karakan in west central Iran, of which the slide shows the tympanum in the later tower on the left, dated to 1093 of the Common Era, in relation to an undated anonymous text exploring geometry of a related pattern. The complexity of periodic patterns of these monuments, that of the mihrab of the later tower at Karakan on the left with six-fold symmetry, is treated in relation to the complexity of both periodic patterns and quasi-periodic patterns, as you see on the right at Merageh in the Gumbadi Kabud. The rich variety of tilings and tessellations are presented in my book in consideration of their architectural and cultural contexts. The complex patterns link the visual expression of forms not only to geometry in the histories of both architecture and mathematics, but also to contemporary philosophical discourse and the development of Arabic poetics and Persian poetry. Disciplines that are too often approached in isolation from one another. I seek to bridge what I recognize as a scholarly gap that exists between those who relatively exclusively rely upon textual traditions and those who draw from visual sources. In the absence of treatises that relate these traditions, such as those of Alberti and Vitruvius in the West, we must carefully amass the visual data and its interpretation, utilizing the ornament of standing monuments and their analysis and documentation as our primary sources. One of the interesting connections that I've come across is Plato, who died in 347 before the Common Era, who in his late dialogue, Timaeus, brilliantly proposes two ideal triangles. And he challenges anyone to prove him wrong or to offer better examples. You see these triangles on the left of the slide. One is half an equilateral triangle, the other half a square. Thus, the first is a scalene triangle with angles 30, 60, 90 degrees, and the second is the right isosceles triangle with angles of 45, 45, 90 degrees. In both cases, the sides are incommensurable. That is, they are not expressible as a fraction of natural numbers. Today, we know that with a unit side, the first produces a ratio of 1 to the square root of 3, and the second produces a ratio of 1 to the square root of 2. But in Plato's time, there were no irrational numbers. Nonetheless, with these two ideal triangles, he immediately constructed three-dimensional solid forms, which you see on the right: the tetrahedron, the hexahedron or cube, the octahedron, and the icosahedron, what today, along with the dodecahedron, we call the Platonic solids. But Plato did not consider two-dimensional space or the plane. Plato's works, including Timaeus, were well known in the Islamic world, attested in the Fihrist of Ibn Nadim, which was compiled in the 10th century of the Common Era. At the bottom of the slide, we see Euclid's construction, as mentioned earlier. He was writing in the centuries succeeding Plato. His profound and systematic study of geometry was also well known throughout the Islamic world, with several early translations undertaken through patronage of the court. Throughout his 13 books on geometry, he treated what we now call the Euclidean plane as a limited dimension of line segments and closed figures, such as circle and polygons. Book 1 begins with 20 definitions of basic definitions, concepts such as lines, angles, and regular polygons, but like Plato, he referred to three-dimensional solids and never treated the plane as continuous, with the exception of his parallel postulate, Book 1, Postulate 5, which assumes lines without limits. So I think that the geometry in Islamic geometric patterns that cover the plane, exploring two-dimensional space, go beyond Euclid. Plato's ideal triangles serve as a very important function in covering the plane, and the fundamental principles of geometry, as advanced by Euclid, remain central to geometric construction. Gumbad-e-Surkh at Marrakech is constructed of fire brick. It is one of the earliest Islamic monuments to incorporate glazed brick elements in its compositions. It is cubic in structure with engaged corner columns, double blind arches, and an octagonal transition zone that once supported a dome, now long gone. The surface of this building bears many geometric patterns, all of which are periodic, that is, they repeat, according to the properties of symmetry operations, translation, with corresponding points along a line. The patterns cover the plane, implying extension beyond the arbitrary boundaries of the space designated for coverage. The tympanum above the entrance bears the most complicated pattern. It also bears a historical inscription giving the lunar Hijri date of construction as 542 Hijra, 1148 of the Common Era, and the name of the patron, the Ravam Azerbaijan. The pattern of the tympanum features a composition in clay with three intersecting polygonal networks that comprise intersecting non-regular nonagons, nine-sided polygons, 6 of which together leave a 6-pointed star in the negative space at the center. Note that the nonagons are highlighted in turquoise glaze. A double hexagonal grid, which also implies extension beyond the arcuate tympanum, and intersecting regular dodecagons, 12-sided polygons, 6 of which also leave a 6-pointed star in negative space at the center, having a different orientation than that of the 6 nonagons. The 2 central 6-pointed stars in negative space overlap, creating a 12-pointed star defined in the central zone. This pattern with intersecting polygonal networks on 3 levels is unique as far as I know. Another brick tomb tower at Marrakech. Sorry, these got confused. Can we go back one? Yeah. Another brick tomb tower at Marrakech, Gumbad-e-Kaboud, which is also prismatic in structure, was constructed a half-century later at the end of the 12th century. However, it is decagonal in plan, bearing a pattern that is even more complicated than that at the tympanum at Gumbadi Surg. A rectangular panel on the face of the Gumbadi Kabud is reflected 9 times around the shaft of the monument, but for the entryway with its arched door. Numerous points, lines, angles appear in cut brick on the revetments, creating complicated patterns in the plane, establishing a system of 5-fold repeats. The main pattern on each facet comprises a patch of a quasi-periodic pattern with local pentagonal and decagonal symmetries, which are with reflected repetition 9 times around the shaft of the monument. Although the repeated reflection of this pattern may be seen as periodic, what is repeated is a rectangle that bears the patch of a quasi-periodic pattern, as demonstrated brilliantly by Rima Ajluni in her study of quasi-periodic patterns and their long-range global order. This is considered by some to be the earliest known quasi-periodic pattern bearing local pentagonal and decagonal symmetries. Earlier patterns in cut brick monuments are all periodic. Difficult to apprehend, these geometric patterns, whether periodic or quasi-periodic, affect wonder in those who seek to understand them. The cultural significance of geometry in monuments of the 11th and 12th century is highlighted not only by the architectural ornament, but also by its presence in contemporary poetry and philosophical discourse. Earlier in the 10th century, the Ikhwana Safa, the Brethren of Purity, writing in Basra, carefully considered the properties of numbers and geometric magnitudes as prerequisites to spiritual understanding. They considered arithmetic and geometry as propedeutic branches of learning that could lead to consideration of logic, theology, and metaphysics. They distinguished between the sensible and intellectual geometry, Handasa Hissiya and Handasa Akliya, respectively. In the following century, the mathematician and physicist Ibn al-Haytham, who died in 1040 of the Common Era, postulated an infinite extent of space going beyond the delimited conception of Aristotle's consideration of the term place, topos, that is contained space, space that is contained within a surface such as that of a vessel. Geometric patterns of the plane are also relevant to a conceptualization of the spatial dimension that implies infinite extent. The new conceptualization of space that I identify does not contradict the systematic study of geometry in Euclid's Elements, but it nonetheless goes beyond Euclid's exposition of the plane, which is for the most part limited in his work by line segments and closed figures. The arguments expanded upon both in my paper for this conference and in my book focus on periodic patterns in the plane and what we now call quasi-periodic patterns, which comprise Islamic architectural ornament from the 11th century onward. I have attempted to treat the geometric patterns in a documentary and analytical manner, taking into account accompanying Quranic inscriptions and architectural and cultural contexts. My conclusions suggest that these monuments provide sufficient visual evidence for ongoing study of geometric patterns in the plane, consonant with contemporary scientific inquiry and discourse in philosophy and poetics. Thank you.
Ms. Bier, please, may I kindly ask you to remain on the stage while we are taking some questions from the audience, please? اخواني واخواتي الحضور الكريم، امامكم الرمز الشريطي. اذا ما عليكم امر تعملون مسح على الرمز الشريطي، وبيدخلكم مباشره على صفحه الاسئله. من خلال الصفحه هذه ممكن تدلون باسئلتكم عشان تجيب عليها الاستاذه كارول.
هل سؤال؟ No questions. One question.
Just a minute, sir.
Thank you very much for this great presentation, great breadth also. Maybe I'm coming back to your last statement. I mean, there are two positions in this kind of ornament and pattern studies. One says this has been produced by, let's say, the simple craftsman knowledge of the compass and the ruler, whereas you seem to tend to the second position, which would say it would reflect science of mathematics and geometric sciences at the period, or even larger entities of thought. Could you maybe elaborate on that point?
Yes, it's a very good question, and the answer is not clear, nor am I definite on where I stand. We can analyze these patterns geometrically. We can analyze them geometrically and understand the relationship if we were to construct them with a compass and straight edge. How were they made is another question. And in the case of bricks, the brick is individually set. I call it a unitary and systematic method of construction. In some cases, they were cut. But the process of making a pattern, the process of repeating that unit, no matter what the technology, is what establishes the spatial relationships in the finished pattern. So I think that in part of our discussion of geometric patterns, we need to take into account the process of pattern making, the processes of craft and technology always being a limiting factor on craft production, the differences in that, and yet we have so many of the same patterns in many different crafts. So there's something more than just craft and technology that yields to the production of these crafts. And I call that in my book an algorithmic aesthetic, an aesthetic that itself values repetition. When we think in American culture values or the values of Western art history in Europe, we think of repetition as, we dismiss it. It doesn't have significance. And what I argue is that not only does repetition have significance in an aesthetic based on algorithms and algorithmic processes, but the geometry and these forms bear cultural meaning. Hope that addresses the question. Any other? Okay.